Welcome to this next lecture on acoustics. We are looking at 1D acoustic wave equation. So we started looking at a finite pipe that is driven by a volume velocity source at one end and there is a general impedance at the other end. So we looked at the pressure reflection coefficient expressions at x equal to 0 and x equal to L, and they are related in this manner. Now if you recall the first boundary condition, which is this, okay, let me copy that. Okay, so this was the boundary condition. This was the boundary condition at x equal to 0. So you recall that the velocity can be written as a tilde by rho 0 c minus b tilde by rho 0 c, okay, because x equal to 0 the propagators do not come and I have e to the power j omega t, and that is equal to q0 over s e to the power j omega t. So if I take this out, okay, what I have is q0 is equal to s by rho 0 c into a tilde minus b tilde. Okay. So now I will use this relation over here for relating a tilde and b tilde, so that I get s over rho 0 c is a tilde minus r tilde 0 a tilde, and that is equal to s a tilde by rho 0 c 1 minus r tilde 0. Okay. Now from here and here, from here and here, we can find that a tilde now is equal to q0 rho 0 c by s into 1 minus r tilde 0 and b tilde is equal to q0 rho 0 c r 0 tilde by s into 1 minus r 0 tilde. Okay. So now the a and b's are known. What are we trying to do? We are trying to get the unknowns in terms of the knowns. Okay. See, the known is the driver condition. This is the driver condition, and these are the unknowns. So we have managed to find the unknowns in terms of the condition that we know, the driver condition that we know. Okay. So now if we look at the pressure, that will be given by q rho 0 c by s into 1 minus r 0 tilde and e to the power of minus j k x plus, I can write it as e to the power minus 2 j k l r tilde L e to the power of j k x e to the power j omega t, or I can write this as r 0 tilde from here. Okay. And similarly the particle velocity u tilde x comma t is given by Q0 rho 0 C by S into 1 minus R tilde 0, and because these are plane waves, it's minus jkx, right, going by rho 0 C, and a minus, okay, then I'll put R0 tilde e to the power of jkx by rho 0 C e to the power of j omega t, and this goes, okay. So it's equal to Q0 by S 1 minus R tilde 0 e to the power of minus jkx minus R0 tilde e to the power jkx e to the power j omega t. Okay. So now you can see here that if we have a rigid condition, we have a rigid end condition, we will have this as minus 1, this as a minus 1, RL tilde will be minus 1. So if we have, let me copy this to the other side, then we will see. Okay. So this is my pressure, this is my particle velocity. Okay. So if at x equal to L, if at x equal to L, I have e to the power of minus jkl plus e to the power of minus 2jkl RL tilde e to the power of jkl equal to 0. Okay. So I get e to the power of minus jkl into 1 plus RL tilde equal to 0, then RL tilde is equal to minus 1. Okay, this is not the rigid end, sorry, this is the pressure release, release condition. That means pressure is 0, P is tilde is 0, P tilde at L comma T is 0. Okay. And if particle velocity is 0, at x equal to L, particle velocity is equal to 0, that means e to the power of minus jkl minus R0 tilde e to the power of jkl, that is equal to 0. Then what I have is R0 tilde is equal to e to the power of minus 2jkl, and this is what R0 tilde was equal to RL tilde e to the power of minus 2jkl, and therefore RL tilde is equal to plus 1. That's a rigid end. Okay. So when pressure is 0, okay, P tilde is 0, then del P by del X acquires a maximum. Okay. So at the pressure release end, where pressure goes to 0, velocity becomes a maximum. velocity is the maximum. Whereas at the rigid end where velocity goes to 0, then the pressure becomes the maximum. Okay, that is because when you have a pressure maximum, pressure is maximum, that means the incident and the reflected have equal amplitudes at that point. Okay, so this is the incident and this is the reflected, they have equal amplitudes. That's when you have a pressure maxima. This is where you have a pressure maxima. And what is happening, that means they are in phase. So the incident wave has a velocity that is going rightward, and the reflected wave is allowing a pressure maxima because it has the same phase as the incident. So there is constructive interference of pressure, but then because it is a reflected wave, the velocity due to this is leftward. So these two velocities combine and they give a velocity 0. So where you have a pressure maximum, there you have 0 velocity, and vice versa. Okay, and even by the condition, rigid condition is a pipe is rigid ended, means the velocity is 0. Okay, and what is velocity in the harmonic sense? Del p tilde del x minus j omega rho 0 velocity, or v tilde. So if v tilde is 0, then del p del x is 0. So here del p del x is 0. Okay, and on the other hand, if we have an open ended pipe which is pressure release, okay, there the pressure is 0 and therefore velocity is a maximum. And how is a pressure 0 happens? I have an incident pressure, let us say, that is compressive. Okay, in order to cancel this pressure, I must have a rarefied wave. If I am going to cancel somewhere, this must interfere with a rarefied, okay, negative pressure wave. This pressure is below gauge, okay, below atmospheric pressure. That is how you get pressure 0. Okay. Now this has a particle velocity towards the right, okay, and this has a particle velocity to the left being compressive. So if this is rarefied, it is a suction, then the velocity will switch sign, it will become this way. If this switches sign, then the velocity direction switches sign. So this has switched sign from compression, so it is a rarefied wave, and therefore the velocity is due to this, even though it is going this way, it is rarefied, and therefore the velocity will be this way. So this velocity combined with that velocity, you get a velocity maximum. So where you have a pressure 0 due to combination, there you have a velocity maximum. Okay, so that's the logic over here. Now let us see. I am going to look at the power condition, okay, power in a 1D wave, in a 1D acoustic wave. So now we have, let us see, earlier we saw that the time averaged power time averaged power in a spring mass damper is something like 1/2 f square of over mechanical magnitude square into r, okay, where z mechanical was given by r plus jx, okay. So we'll write this as 1/2 f and then f by z m tilde, then z m tilde conjugate by z m tilde conjugate. So this f and this f give me f square, this and this give me magnitude of zm square, and I have this over here which is r minus jx because of the conjugate, okay. Now I take the real value. So if I take the real value of this thing, I take the real of this thing, then only this will survive, the j will go away, right. So what do I mean? Real of 1/2 f by z m tilde r minus jx by z tilde m conjugate, that is equal to, inside first of all is f square by 2 magnitude z m tilde square. So I have 2 f square z m tilde square, and the real part gets me the r, okay. So what does the exercise mean? This means the time averaged power can be found as 1/2 the real part of f, 1/2 real part of f, and this is this whole thing is V conjugate. This whole thing is V conjugate. Okay. So either, just from the power calculation of a spring mass damper, I have found that the time averaged power from the forcing location is also given by 1/2 the real part of f V conjugate. Okay. So now what we do is we are going to compute the power in the duct, okay. So the time average power is given by this at x equal to 0, okay. Now at x equal to 0, the pressure is given by A tilde plus B tilde e to the power of j omega t, and the particle velocity is given by A tilde by rho 0 c minus B tilde by rho 0 c e to the power j omega t, okay. So now the time averaged power which is this t is given by 1/2 the real part of a tilde plus b tilde. See, this is only pressure, so I need area to make it force. So there is a area to make it a force, time dependence. Now the conjugate of velocity, is a tilde conjugate by rho 0 c minus b tilde conjugate by rho 0 c e to the power of minus j omega t. Okay, so this j omega t and minus j omega t go away. Okay, so what do I get here? I get 1/2 the real part of a times a conjugate is magnitude of a tilde square by rho 0 c, and b times b conjugate with a minus magnitude of b tilde square by rho 0 c, and then I have minus a tilde b tilde conjugate plus b tilde a tilde conjugate by rho 0 c. Okay, so this is a conjugate of the other with a minus. Okay, so if this is x plus iy, this is x minus iy. So if a tilde b tilde conjugate is x plus iy, then a tilde conjugate b tilde is conjugate of this x minus iy. So if I subtract, I get twice iy. Okay, so I get twice the imaginary part of this quantity over here. So it carries an I with it. Okay, and I am taking a real value over here. So the real will take out the imaginary quantity. So I get 1/2 the real part of magnitude of a tilde square by rho 0 c. There is an s over here, so let us put that s minus b tilde square by rho 0 c. Okay, so it's a very neat expression. Okay, in 1D plane waves. In 1D plane waves, the net averaged power expended by the source, okay, expended by the source is right travelling wave power minus left travelling wave power. Okay, averaged. So this is magnitude a square s by twice rho 0 c, and this is magnitude b square s by twice rho 0 c. Okay. Now we can further write this as (1/2 S by rho 0 C magnitude of A square minus magnitude of R0 square magnitude of A square, or 1 by 2 S magnitude of A square by rho 0 C 1 minus magnitude R0 square. Okay. So now you can see that if R0 happens to be plus or minus 1, okay, then this thing is 0. Okay. Why? So this happens to be either the rigid ended condition, that means velocity is 0, velocity at L comma T is 0, or the pressure release condition, where pressure is 0. Okay. Under these conditions there is no dissipation, and therefore magnitude of B is going to be equal to magnitude of A. Okay. So all the earlier ideas come up, and therefore the averaged power is going to be 0. Okay, under such conditions. Okay. Now the power reflection coefficient, is given by R pi, which is equal to power in B by power in A. Okay. And then the power in B is S by 2 rho 0 C magnitude of B tilde square, power in A is equal to S by 2 rho 0 C magnitude of A square, and from here the power reflection coefficient is squared. Okay. So this will be non-zero, or this will be less, this will be less than 1, this will be less than 1 if there is a dissipative end, boundary condition is dissipative. Okay. So another situation is where I have again a one dimensional duct where there is a power incident. Okay, this is equal to incident power. Okay, and now there is some material along the pathway, so that there is a transmitted power, and there may even be some absorbed power, and there is a reflected power. Okay, so that the power incident is power transmitted plus power reflected plus power absorbed. Okay, or dividing by incident power, we have 1 is equal to transmitted power coefficient plus reflected power coefficient plus absorption power coefficient, and if there is no absorption, then we have 1 is equal to transmitted power coefficient plus reflected power coefficient. Okay. So, this is the solution to a 1D acoustic wave in terms of the boundary conditions and in terms of the source. Okay. And the boundary conditions come in terms of this reflection coefficient, and source comes as a volume velocity source. Okay. So, with this I will close the 1D acoustic portion. What I carried out here is more than what we did with strings and bars. So, with strings and bars we looked at the 1D equation and many things came out. Those things still apply here, but in here we did a little bit more, where we solved the pipe unknowns or duct unknowns in terms of this reflection coefficient at one end and the source at the other end. Okay. In the next class we will look at the green function. Thank you.